Hello, good morning, good evening, good afternoon, good day, wherever you are in the world, and we're back again for another live stream. We have CJ here again today. We're gonna have a lesson, so just tune in and listen. And yeah, if your question is about what we're doing on the stream, we'll go ahead. And if you're done with the stream, I'll answer your other questions. By the way, today's topic is the same as yesterday's, which is electricity and magnetism. Because that's what our student here today, CJ, is gonna do soon. All right, let me just get to the before we get to the board. Let's see if he's in yet. He's not in yet. Let's join the lesson either way. And the camera there's not on yet. Okay, here we go. Hmm. Apparently we dropped a few frames already. Hmm. Okay, nobody's in the stream yet. Let's just keep talking while we're waiting. All right, so just I've been having a few ideas on. Okay, never mind. CJ's here, so let's talk about those ideas later. All right,
Hello.
hi CJ. Good evening. Can you
Good
hear
evening.
me? All right, can you hear me clearly?
Yes.
All right, good. So yesterday we ended at answering. What question was that? Hold on. Okay, I think we finished with. I think this set of papers. All right. There we go.
Oh, also from what you said
Mm-hmm.
today, um, is the lesson from 7, that starts at 7,
Mm-hmm.
was that from this Sunday?
That's a Sunday, yeah.
Or is that also,
So if you want to reschedule
oh,
that,
it's also
that's
on
fine.
Sunday. Yeah. I didn't know
Okay.
I changed it for all of it.
All right. Okay, but I'm. Here's the thing. I'm actually studying for something, but it's fine because I can always work around another schedule. So Sundays I'm okay with moving Sundays, but weekdays rather. Yeah, we have to do it like this right now. Except for Thursdays, I
Mm.
kept the schedule for Thursday for us. Okay.
Okay, so we have to move to Thursday?
No, the Thursday's fine. Don't worry about Thursday. Let's just go back to the calendar. No. If you look at the calendar, you see that it's like we have a lesson at 5 to 6 on Sunday, and then we
Mhm.
have a 7 to 8, right? So there's like a 1 hour gap between the lessons.
Yeah.
Okay. It's if it's okay with you, we could move one of those lessons to 6 o'clock.
Yeah.
So which one would you
Sure.
rather move? The 3 o'clock, the 5 o'clock, or the 7 o'clock
Oh, ooh. I think I have a driving test
on Sunday?
on Sunday.
Okay, so we'll move the 5 o'clock one. Yeah.
Yeah.
Okay, there we go. So on the 25th, that's on Sunday, we're gonna be together from
Yeah.
6 to 8.
Also, I can't on the 29th,
On the 29th, you can. All right.
Thursday.
Uh, okay, let me just update this. Okay. All right. And then on the 29th, you can't really have a lesson. So would you like to move that to another time?
On the 29th.
That's a Thursday. So you can move it to Sunday again, or you can move it to another date later on. Another date.
Oh, sure. Um, Sunday you have a lesson at 6.
That's you.
Oh, that's
Actually,
me?
no, no, no.
Oh,
That's I could move that to 6. It's fine. I could move that to Sunday on 6. It's okay. I can reschedule this
okay,
with you.
sure, yeah.
All right. So for now, I'll just move it to Sunday at 7 because I need to update my Google Calendar. But for now, I'll just move it to Sunday at 7. I'll move it again once I update the calendar. Okay.
Okay.
All right. So schedule. Okay, rescheduling. All right. I'll just reschedule this lesson on the 3rd of March. Right. The 3rd of March. It will be rescheduled later on.
Yeah.
Okay then. So on Thursday we have one lesson, and then on Sunday we have 2 hours. This coming
Mm-hmm.
Sunday. All right, great.
Because Thursday's after my test. Yeah.
Mm-hmm. All right, sure. Let's see now. So this is gonna be our last meeting before your test. Tomorrow's your test, right?
Yes.
All right. And how are you feeling about it?
Not too bad, actually.
That's good. All right. So let's move on. The the board's been shared with you on the chat box, so you can just check it out over there.
Thank you.
All right. We're still doing electricity and magnetism. Let's look for that question. Here's a magnetism question now. Okay. I think we better put some more magnetism questions in. Okay. So the first part is you have an electron. Now, if you haven't noticed it yet, you notice that about 80% of the questions with electricity and magnetism always involve electrons, right?
Oh, really?
Yeah, especially with magnetism, we usually learn about it using positive charges, but the exams always give us like electrons. Okay, so anyway, here's the first problem here. That's a given information. First of all, the first question is state the direction of the magnetic field for 1 mark.
Oh.
Okay, so remember that this electron moves in a circular orbit or a circular motion in a uniform magnetic field.
Hmm. Oh, the direction. Okay.
Mm-hmm.
Not bad. Hmm.
Doesn't You don't have to calculate anything yet.
Uh, the velocity?
Mm-hmm. The velocity at point P of that electron is given to be on the right. That's what it means. But
Do I
of
use
course,
my right hand for this?
yes,
So if velocity
I'm gonna give you a
velocity,
clue.
does that mean like the force in that
Mm-hmm.
direction?
Mm-hmm.
Oh,
I'll give you a clue
I'm
right
not
now.
trying to
Okay,
yeah. Yes.
it's moving in a circle. That's your clue.
Oh, state the direction.
Mm-hmm.
Circular. Wait, no, no. Um, is it out of the page? I don't know. I want to say out of the page.
Okay. Um, it's definitely either in or out of the page, right?
Oh,
Uh,
wait. Okay, if it's in or out, let me think about it. Oh,
yeah, you're right. You have to use the left hand.
oh, left hand.
Mm-hmm. Left hand. Okay, left hand.
Um, Wait, but this is electric field. Wait, force. Where's the force going? The force is going where the velocity is going, right?
No. Circular motion is the clue here.
I'm so confused now.
Okay, here's I'll give you the answer when it comes to that, but it's still not the final answer. Remember that in a circular motion, the force is always directed towards the center of the circle.
Mm-hmm.
So where P is
Center.
right now, where the electron is right now at point P, which way is to
That's
the
the
center
center.
of the center of the circle?
Up.
It's up. So the
Oh,
force
is that the
is
answer?
so the force is directed upwards, but the question is about the magnetic field.
Oh, then the magnetic field is going up. Wait, no, out. No. If the magnetic field's going down, wait, this is up. It's either the force is up in both directions.
Aha. The force is either way, the force is up, right? So which way is
Oh,
our current? Is it to the right or to the left?
to the right.
Uh-huh. Why do you say to the right?
Because if the current was going any other direction, I feel like the electrons would move in that other direction.
Okay, but remember it's already an electron to start with.
Yeah.
So if the electron's going to the right, the current is going the other way.
Left?
It's going to the left.
Wait, wait, what?
All right. I think I better go explain that. Okay. So whenever there is um in a wire, let's do this in a wire, but this actually works for any situation. Let's say that you have a wire here, right? Okay.
Mhm.
Now, what actually moves in a wire? Remember, you have your um atoms here, and they're in ion form because the electrons are freely moving. So they're positive, right? And then your electrons are gonna be, let's say these are your electrons, okay? And these electrons are negatively charged. At least that's what we know now. They're negatively charged, right? So
Mhm.
if the current is flowing, let's say that the current is flowing this way. Which way are the electrons moving?
Um, left.
They're moving to the left. The electrons are going that way. So in other words, what do you always think? It doesn't matter whether we're talking about electric
Oh,
currents or free moving electrons or whatever. The idea here is the flow of the conventional current, and I'm gonna put conventional in current in quotes, is opposite the flow of electrons. Okay, why? Because the conventional current is regarded as the flow of positive charges. Okay, so this would be the flow. Okay, and I'm gonna put that in quotes. The flow of positive charges. Okay, electrons would be, of course, the flow of negative charges. Okay, so with that in mind, whenever you see anything about electrons and positive charges, if you see an electron, you instantly assume that the current, whether it's a true current or the current for the magnetic field thing, is the opposite way. Okay, so if we go back here, we
mhm.
know that this is an electron. Okay, if that's an electron moving to the right, what's the equivalent of that? It's a current moving to the left. Okay, all right. So with that in mind, either way, I think you got the idea that you have to use the left hand rule and you need to
Mm-hmm.
kind of find the direction using the left hand, right? And you said, okay, let's do it the way you did it before. You said that the velocity is pointing to the right, so that would be the current, right? So right would be the middle
Yeah.
finger, and then the force is pointing up. So that is correct. So force is up. We don't know magnetic field yet, but the current is to the right. I'm gonna go like this so you can see that. And as you can see, the magnetic field is pointing into the page, right? So you said in, so using that was correct. So at least you did it correctly. The thing that you missed is the fact that it's an electron. Okay. So in this case, the magnetic field is pointing outward of the page.
How do you make it point out of the page?
Okay, so all right, let me go to the big screen first so you can see that. Okay, so first of all, velocity of the electron is to the right. Okay, am I
Mm-hmm.
pointing the right direction? Okay, yeah, it's pointing to the right.
That's the right. Wait, do I
Okay,
use my right hand or left hand in this
left hand,
case?
left hand.
Left
Okay,
hand.
so so we need to use the middle finger. It's pointing to the right, but it's an electron, so you make it go the other way. So you make the electron point to the left now. You make the current point to the left now because it's an electron. The force is still up.
Yeah.
The force is still up. So which way does
Yeah.
it point? It points to you. It points out of
Straight.
the page.
Okay.
Okay.
Out. Wait, then I can use my right hand in this case.
If you use your right hand, you're gonna have to reverse a few things. You're gonna start with the F on the middle finger.
Okay.
Okay, but aside from that, if you want to use the right hand, it's okay. Just make sure that F is the middle finger. Okay.
Oh, is that what that's what you mean?
Mm-hmm.
But instead of like showing it like that, I feel like this shows exactly what you're trying to explain. Like current going that way, but velocity this way.
Mm-hmm.
An electromagnetic field, and here's force. So if I know that if the velocity is this way, could
Mm-hmm.
I just no,
Hold on,
maybe
hold
not.
on. Do that again so I can see it.
So I was like, if you know current this way, but you
Mm-hmm.
want to talk about the electron's characteristics,
Mm-hmm.
could I just be like velocity?
Oh, I see what you mean. Yes, you could do that.
Hmm.
Okay.
But when would you use the right hand?
Um, I guess from the way you're doing it, okay, from the way you're doing it, you would use the left hand for positive charges and the right hand for negative charges.
Okay.
All right, but basically that still means F is the thumb, B is the middle finger, I is the current. Okay, hold on, man. Hold on. All right, never mind. Okay, so all right, so sorry about that. My kid's asking for. Well, I'm limiting her screen time, and since she did her work, I'll give her some extra time. Give me like 30 seconds.
Okay.
All right, where is it? I'll give her 30 minutes for now. All right, done. Let's continue. All right, let's continue. So the next question is calculate the magnitude of the magnetic force on the electron in newtons. Let me just put that on the screen too. Again, so calculate the magnitude of the magnetic force on the electron. I think I need to get some information from here. It's this. Okay. Okay, so So again, the velocity of the electron at point P is that much, pointing right. Okay. And the magnetic field is here. And we know that the magnetic field is pointing out of range, right?
Mm-hmm.
Okay. Oh, by the way, if you get this previous answer wrong, it doesn't matter because the the direction doesn't really matter here because we're looking now for the magnitude, right? Okay. So anyway, what would the magnetic force on the electron be? Uh,
Um,
remember the formula?
wait, where's my calculator?
It is my the booklet.
Oh, your screen disappeared.
Hold on. Let me go pick that back up. Yeah. Okay. Remember that this is an electron, so that's one hint as well.
What's the hint?
Okay. So the hint is, of course, we have your stuff here given. The hint is again you have an electron, so you should know something about that.
Hmm. I think we use QVB sine
Mm-hmm.
theta.
Correct. Correct.
Q is negative 1.6
Mm-hmm.
times 10 to the negative 19.
So correct. So let's put that here. Q is equal to 1.6 times 10 to the minus 19. And let's write the formula. F equals QVB. Right.
Um, sine 90, I assume.
Uh-huh. It is.
Negative 8.27 times 10 to the negative 13.
Okay. So put the values in there. Just four, right? Uh,
So the magnitude, it's okay if I have a negative, right? Because it shows
yeah.
the direction.
Yeah, because the negative just gives you the direction somehow. In this case, the answer is negative. Gonna be 0.37. Oh, sorry, wrong thing. B. 9.2. 9.2 times 10 to the minus 13.
9.2?
Mm-hmm.
I didn't get 9.2. I got 10 to the negative 13 though.
Yeah. Uh, okay. I'll just show it in the calculator, see whether we get the same numbers. Yeah. So for your Q, you use 1.6 times 10 to the negative 19, right? And then
Yes.
your V should be there 6.8 times 10 to the 5. 6.8
Oh,
expand
wait. Sorry.
5.
I was in radians.
Oh, you were in radians. Okay. All right. Now, if I were you, most problems ignore this. Okay.
Yeah.
So,
Unless said so.
yeah. Let's just put the B in. B is 8.5. So if we finish the calculation times 8.5, yeah, 0.9248. Okay. So this is correct. So your mistake was radian mode. Yeah.
Mm-hmm.
Okay. Radian mode. Now, I would suggest something. Okay. Okay. To avoid this in this problem, this is automatically assumed. Automatic. Okay. You don't have to assume angles at this point unless it's given to you. Okay, unless given. Okay, so in other words, because you're gonna do sine of 90 degrees, that's just one anyway. Unless you're given some sort of angle, it's going to be always QVB. Okay, so you don't have to think too hard about this. Don't do the sine of 80. Okay, just to make it faster, if nothing else. Yeah. All right. Next. Ah. All right. Next question is about how the electron moves. First is explain why the electron moves at a constant speed. And then the next bit is why does the electron move on a circular path? Okay, I guess the constant speed thing is a bit easier,
Mm,
but the circular
because
path.
the current.
Okay, go ahead.
Why is it because of the speed? Can it be because there's a constant attraction,
Mm-hmm.
or because the current doesn't change?
No,
No.
not that. It's not that.
Is this something about attraction?
Also, no.
Never mind then.
All right. Okay, I think I'll give you a clue here. Think, think of a satellite going around the Earth.
Mm-hmm.
Okay, just think of it like that. If the satellite is moving in a circular orbit, it's not getting higher, it's not getting lower, right?
Yeah.
So does it have is anything doing work on it? It's not. It stays in a
Oh,
constant height above the Earth, right? So it's not
yeah.
gaining any potential energy or losing it for that matter, right?
Mm-hmm.
Similarly, that thing in when something is in a circular path, most of the time, if the force is constant, the speed is constant, right? So,
Yes.
okay. The idea here is if something is moving in a constant speed in a circular path, okay, so let's do this here. Things moving in a circle, objects moving in a circular path with a constant speed, experience two things. They experience a force directed towards the middle, right? Or again, towards the center of the circle. The thing here is, if you think about it a bit more, there are two possible ways that you get to the same conclusion, and the conclusion will be, I'll just put the conclusion now, there is no work done on the object, okay, by the centripetal force. So that's the idea. So again, there are two ways we can go around it, but the conclusion is the same. There is no work done on an object by the centripetal force. Okay. Well, the first path is thinking about it this way. Remember that if you look in the data booklet, let's see if it's in there in the data booklet. Topic 2, work done. Okay, in topic 2, work done is equal to force times distance cosine theta. There's a cosine theta to it, right? Right, and the thing here is F and S. We're looking at the F and S components that are parallel, right? Parallel. Okay. So if that angle between the force and the displacement is 90 degrees. So um in if it's 90 degrees, then what's gonna happen? There's no work done, right?
Yeah.
But the thing here is F is always perpendicular to velocity, right? Which means that F is perpendicular to that displacement for that short amount of time, meaning work done is zero. So that's one way for you to remember that. Okay. The other way, and this is the more intuitive way of saying it. Okay. Um, we know that for objects moving in a circle, um, their speed doesn't really change, right? So speed doesn't change means ke is constant, right? And then the circle is a constant distance from the Earth, for example. So in this case, the potential energy is also constant. I think this is the more intuitive way of saying it. K is constant due to constant speed, right?
Mhm.
Okay, and potential energy is constant because of no change in uh, no height gain, right? Or loss. Especially if your object's right in the middle of the circle, right? So if this is your object, that's your circle, that's always going to be a constant distance. This is r, 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 r. It doesn't change. So no height gain, constant speed, no work done. Okay. So going back to the question, so why does the electron move at a constant speed? Which one is the better explanation in this case, though? Is it the force thing or is it the energy thing?
Um, the work isn't done.
Mm-hmm.
Oh, it's at the constant speed because no work is done.
Okay, but which of these two reasons is the better reason to quote here? Is it the force is perpendicular to displacement, or is it that Ke and Pe do not change? Which one's the better one to go through?
Mm, force is perpendicular to
Hmm.
displacement.
Yeah, that's actually the better answer to go to here. Okay, so force
Yeah.
is perpendicular to um the speed, so no speed gained, right? Sorry, velocity. Let's even use the word velocity. Velocity, and therefore no speed gained. So there, that's
Speed
it.
is a scalar, right?
Hmm. The velocity changes because the direction changes, but the speed itself doesn't change.
Hmm.
Okay. All right. How about this one? Why does it?
Uh,
Okay. How about the second one? Why
is
does
it
it move in a
circular?
circular path?
Um, okay. Does this connect to what you just said?
Yes, it's still connected to that.
Um, can I say because it's in a circuit, it's in a loop?
Uh huh. It's in a circular. You, it's better to say it's in a
So the
circular
sec.
path. So
Oh, why does it say circular?
because it is in a circular path. Let's go back to the problem.
In the wire as
It's
well.
this. Remember, this is not a wire. This is an electron in an electric. Yeah, in a magnetic field. It's
Oh,
not in a wire.
okay.
Okay. So going back here.
Because of a because there's no work done on the object by the centripetal force.
Mm, not really.
Um, is this something about attracting and repelling?
No, not as well. Okay.
Constant speed.
Now,
Hmm.
here's the thing. What is the condition for circular motion? What's the main condition?
Like it like orbits around something.
Okay, so that's one. But the main condition is that the force is perpendicular to the speed. That's the main condition. So that's why I said it goes back to this idea. It goes back to going here. Yeah. So the answer here is that I'll write the answer down. Okay. The answer here would be uh since force is perpendicular to speed, uh force is therefore a centripetal force. which makes the electron move in a circle. Move in a circle. Okay. So again, so why does the electron move at a constant speed? Because there's no work done on the electron, so its speed doesn't change. Why does the electron move in a circular path? Because the force is perpendicular to the velocity. Okay. All right. So let's see if I can get to another problem like that. Is there anything else that I can get to though? No. All right. Let's go on to the next problem. This is circular motion, forces, energy, ideal gases, waves, electricity. That was electricity, right? We'll skip electricity for now. Let me get another set of problems for. Yeah, okay. This is that. That. Bouncing. Ideal gases. Okay. Electricity. Magnetism. Here's a magnetism problem. Okay. So the first one, the setup is this. You now have a proton moving on a circular path in a uniform magnetic field. So this is going to be really similar to the previous one. Yeah. Okay, so there's the setup. The image is here. Okay. So first of all, draw the arrows for the magnetic field, a magnetic force rather, and the velocity of the proton. Again, label with arrows on the diagram the magnetic force and the velocity vector of the proton. Again, your big clue here is that um, it's moving in a circle. You'll get a lot of these questions later on, yeah. Magnetic fields of stuff moving in a circle.
Is the magnetic force on F like pointing outwards?
No, it shouldn't be
It's
pointing
not.
outwards.
It's pointing inwards, really?
Yeah, why does it point inwards? Because it's moving in a circle.
Oh, that's what you mean.
Yeah,
Oh, okay.
inwards, circular motion, right? Remember, in circular motion, the force is always towards the center.
Mm-hmm.
So in this particular case, because you need to draw here, you would have to draw it something like this.
Mm-hmm.
And that's F. Okay. How about the velocity vector? This is now where you can use something. I'll not tell you what it is just yet.
Use something?
Mm-hmm. We've used it before in the the previous problem.
F is perpendicular to V.
Mm-hmm. But if you only use that, there are only two possibilities. You need to narrow it down to to one, right? So what are the possibilities? That's the first
Displacement.
possibility, and that's the second possibility.
F
You have two
F is directly proportional to
because
displacement.
mhm, because both of these are
Mm.
perpendicular to the force, right?
Mm-hmm.
So which one is correct? The one going downwards or the one going upwards? What do you do? All right, I'll give you one clue. That's your magnetic field right there.
Yeah.
Which way is it pointing? Down, into or out of the page?
But magnetic field.
Mm-hmm.
Um. Oh, is it pointing out? No,
No.
out of the page.
Check. Are they dots or crosses?
Those are crosses. Are those
Those are
what is
crosses. So let's zoom in a bit. Yeah. So if I zoom in, you'll see that they are indeed crosses. So if they're crosses, that means which way is the magnetic field pointed? Is it in, oops, or out?
what are the two? There's crosses and there's what? Circles?
The okay, there's crosses and then there's dots.
Dots.
Hmm.
Dots.
Have I taught you this, like how to remember which one is which?
No.
Oh, I haven't. All right. Think of these as an think of arrows as arrows, right? So the easiest way for me to actually emphasize this point is for me to get, I guess, this syringe is gonna work. Let me go back. Let me get to big screen first, the camera. Okay. All right. So I have a syringe. Okay.
Oh yeah.
All right. Which way is the syringe pointing right now, from your
On my
point of
screen
view?
or your screen?
Your point of view.
Oh, right.
It's pointing to the right. Okay. Okay. That's pretty obvious, right? If you do it this way, it's pointing to the
Left.
left. Do it this, up, down,
Up.
right? What?
Down.
How do we know those directions? We basically have a head and a tail, right? And the head
Mm-hmm.
and the tail tell us the direction. So it's always pointing like this, in this direction towards the head and away from the tail, right?
Mm-hmm.
So what do you see here? And I think
In.
this is in. And what do you actually see there? You see a
The
cross. What do you see
oh,
here?
the
When's
dot
the
out.
dot? There you go. That should make it easy for you to remember which one is in, which one is out.
Okay.
All right. So going back, is this in or out?
This is in.
This is in. Correct. So this is in. So what do you know? What do you now know? You now know the force. You now know the magnetic field, the
Magnetic field.
directions, right? So which one do you not know yet? You don't know the current or the direction of the velocity, right?
Well,
But if you know two, you can know the three, right? You can know the
wait,
third.
F. Wait, F is like
Positive, left hand, thumb. FBI, right?
I is like going up though.
So which? Okay, let me try to do this. F is to the center, right?
Yeah.
I'll do it out of your field of view first, so from my point of view. And then B is going in. So it is going up, right? So which of these two arrows is up?
Up is the
The
yeah,
top
the
one,
top one.
right? So that's your answer. That is your B.
Wait, so protons go along with the current.
Yes, because they're positively charged.
Okay. But in a circuit, you said they don't move.
Yeah, in a circuit they wouldn't move because they're stuck. They're stuck in place, right? But of course,
Hmm.
in this particular case, what's happening? It's actually a proton moving through space, and in that space, there's a magnetic field. So you can think of
Hmm.
it like a hydrogen nucleus just passing through.
Yeah.
Okay, so it's not just any particular group of protons. It's just that. Okay. All right. So anyway, next problem here. Uh, okay. Mark is on the stream. Mark is one of my students, and he just said he's working on one of his yeah, he's working in his criteria B right now. Keep working on it, Mark. All right. So here's the next question. I do hope my grade 12 students are here. This would be helpful for them right now. Anyway, here. So the speed of the proton is given there, and you're also given the magnetic field strength. So for this proton, determine the radius of the circular path to an appropriate number of sig figs. Which one is
Um,
this?
QV, QVB.
Correct. You're still gonna use F equals QVB, right?
Because it says, okay, whenever it says proton or electron, my default is QVB.
Correct. When you see current, you default to BIL. Yeah.
Oh, yeah.
Okay. So, what's our Q? This is a proton. This is automatic.
Is this a past paper question?
Yes, it is.
No way. All you do is plug it in, though.
Yeah. I'll tell you the source later, but yes, this is a past paper question.
My
Y-
teacher never gives me these. My
So,
teacher is always like picking the hardest of the hardest.
well, I know how your teacher thinks because I think that same way. But for exam questions,
Let's move on.
no. But when it comes to exercises, I usually give them the harder ones. But when it comes to actual paper practice, I give the past papers. All right.
Wait, so exercise, you give harder ones? And
Yeah,
the,
for exercises, I usually give harder ones along with the easier
uh,
ones.
okay.
I usually try to sneak in one or two university level questions.
Oh, that's brutal.
Yeah. Anyway, what's the answer here?
1.45 times 10 to negative 14.
Okay, 1.45 10 to the negative 13. I am not feeling like calculating that. I'll just look at the mark scheme. All right. Sorry, what's your answer again?
1 point, wait, okay, 1.45 times 10 to the negative 14.
14. And this would be in newtons, right? Oh, sorry, meters. Because you're looking for the radius, right?
Yes.
Okay.
Wait, this is the radius?
You're looking
This
for
is
the
the,
radius. This is not the radius because this is force, right?
oh,
But look, you're looking for the radius.
oh, then there's more to do.
Yes, that makes it 3 marks.
Oh, okay. Well,
Well, at least you got 1 mark already.
uh, oh, is it F equals K Q1 Q2 over R squared?
No, no, because you don't have another
Oh,
charge here. I'll give
I
you another
don't.
clue. I give you a clue. Circle. It's a circle. That's your clue. If you see a circle, you must
Okay.
default to another equation for circles.
G equals F over M. Wait, no, that's
No,
math.
that's mass. That's gravity.
A equals V squared over, no. Oh, MV squared over R. No.
Yes.
Yes, yes, yes. Okay, got it. I think.
mv squared over r. Right?
Times.
And then you put that in there, right?
I'll do that.
I would personally not do that straight away. I will not solve straight away. I look for stuff that cancels out first.
Oh, there's things that cancel out right now.
Yeah, I'll show you right now to make it faster. Yeah. So in this case, you're gonna equate the two forces. Centripetal is equal to magnetic, right? So what's gonna happen here? Centripetal is mv squared over r, and then magnetic is qbd, right? What cancels out? One
Mm,
of your v's cancels out with that v.
yeah.
So we're left with mv over
Wouldn't the
r.
mass cancel out as well?
No, there's no mass in the magnetic force part. No mass, so it doesn't cancel. Okay,
Oh, is
mv
that the
over r.
charge?
Yeah, qb. Right. Since we're looking for r, we do r equals mv over qb. The thing is, this is given in the problem. This is given in the problem. Q is in the data booklet. Is also in the data booklet. So all of these are in the data booklet or given.
Hmm.
Okay. So I'll make this a bit quicker. I'll just tell you the value of the.
I got 0.53775.
Okay, 0. Say it again. 0
53775 or just
0.537.
538.
Okay, you got.
0.538.
So in this case, um, R is 0.538 meters is correct, but you only get 2 marks.
Oh, because unit?
Sig figs.
Sig figs. Okay.
Appropriate number of
It's
sig
three sig
figs.
figs.
Okay, two. You must use two.
Two decimal places?
Two sig figs. Why?
What? Oh.
All right. Let me show you why. This is three sig figs, right? This is
Yeah.
two sig figs. You always follow the least number of sig figs.
Okay.
So
Oh, you said that before.
yeah, follow least number of sig figs, right? So this has two. This has three. So final answer must have two.
Hmm.
0.54 meters to sig figs. Okay, two sig figs. All right. Okay, good. Uh, do I have one more problem? I think that's the last question there. Yeah. Let me see. Do I have another problem to go through? We can do one more. Uh, I have electricity, Feynman diagram, double slit. I think we're okay. What I'll do here is I'll put the other electricity problems I've encountered. I'll put them into the Jamboard. You can try to do them later on your own. Yeah.
Thank you.
I'll also be putting the final answer only, and see whether you got the final answers. Yeah. All right. So with that,
Mm.
anything else you'd like to ask before we end today?
No, I think it's good.
Okay. So good luck tomorrow, and see you on the other side.
Thank you.
All right. Bye bye now,
Have a
CJ.
great.
Have a good evening.
See you.
All right, bye. The All right. So that's the end of the lesson. Thank you, CJ, for attending today. Okay. Mark, if you're still there, keep doing that. If you're not done yet, okay? It's not that difficult, I think, but okay. Anyway, back to the stream real quick. I was saying earlier, what was I saying earlier? It's about, let's go back through this. It's about the stream. Uh, I, I kind of thought about, okay, I've been trying a few things to do the stream now, just so we're clear. These live streams and live sessions are still going to be the main thing. So don't worry about this disappearing for anyone who's listening. Of course, if you're not studying that particular bit yet, it's okay. Just listen in and you could learn one or two things, right? But for the other content, especially the shorts, I'm still continuing like the summaries of these things as well, of these live videos. So like getting like the best parts, turning them into shorts. But I was thinking as so I'm gonna introduce two things into the shorts. The first one is a reaction video to, I don't know. Well, I was thinking anime because I'm a weeb. I'm not that hard of a weeb, but still I'm a weeb. Right. So anyway, so that's the first one, and the second thing I was thinking of is experiments, like actual experiments that um you you could either replicate at home or is a cool demonstration of some concept that a lot of people kind of like gloss over. Like for example, here's a good example. W- Why is it that gravity seems to be attractive or something like that? I'm not gonna do that soon because it's a bit complicated. But the idea is, why is gravity always attractive? Well, the answer is we don't know. But if we compare it to some other forces, we can see how it works. and we can see how the equation works, and you will see that no matter what you do, the equation will always tell you that gravity is attractive. Okay, so something like that. So okay, so of course, if anyone has an idea or a suggestion, we're more than open for those suggestions. Uh, Especially for the shorts that I mentioned. What shorts do I mean? The anime based one. Okay. I already have a student. Okay, most of before that, most of you already got to see, if you're still there, most of you already got to see the One Punch Man shorts, right? Yeah, something similar to that. I'm gonna continue doing that series. Okay. If you have any suggestions for anime, yeah, and I am partial to anime here. I don't want to do Hollywood because a lot of people do Hollywood. I want to stick with anime for this. Okay? Now, I was already thinking. Here's the other students. I suggestion. Wait, let me see the suggestion from my student. Okay. Right, here we go. Basically, Satoru Gojo uh from Jujutsu Kaisen. Okay. Specifically, Sat Gojo Satoru's what's this? Limitless powers. Okay. Those are actually pretty good. I've looked at them already, and I think we can do the physics out of that. There are a few people who've done the physics out of it as well. I'm gonna put my spin onto it. Again, if you have any other suggestions, you're more than welcome to. Yeah, yeah, you're more than welcome to suggest, and if they're good, they're good. I got a suggestion from Facebook. I do Dragon Ball, and then I got another YouTube suggestion. It's an extension of the Saitama thing or the One Punch Man thing. Instead of going from the moon to the earth, he actually, in the manga, One Punch Man already has to jump from the sun to the earth, or from Jupiter to the earth. So how fast was he going then? All right, well, or I could explore another thing. Instead of the speed, I could explore like how much energy would that be require, and what equivalent would that be if that was done on Earth. Okay. All right. So with that, I guess we'll end the stream. Let me just see before we end. All right. So again, for those who are new, for anyone new, don't forget to like and subscribe us on like and subscribe to us here on what's this, YouTube, Facebook, or Freaky Physics in TikTok, or Freaky Physics in Instagram. Uh, Another feature, I think I'll add an image here for Freaky Physics. Don't forget to hit the notification bell. Notify. So whenever we're up, you get notified, and then you can join the stream. Okay. Uh, Also, if you wanna go on Twitch, you can do so. What I know, okay, I think I'll use a feature on Twitch wherein it's just gonna loop. No, not gonna loop, but it's gonna play one of the videos every time we're not live. All right, so I guess we can end it here. So again, for those who are here, thank you for joining us. Uh, don't forget to follow us on the social media platforms. And until next time, stay freaky, everyone. Have a good day, good night, good evening, good morning, whatever you are in the world. Bye bye now.